It's angular displacement. Let's tackle the first one, the chapter 2 problem first. We're given initial velocity, acceleration, and time, and trying to find displacement. Which equation do we use?
The displacement equals initial velocity times time plus 1/2 acceleration times time squared.
And so we end up with 5 times 10 plus 1/2 negative 3 times 10 squared, which is 50 minus 150, negative 100 units.
Meters.
What's the answer to this one?
Same thing. Same thing.
Same thing, but different units.
So what is it?
Negative 100 radians?
Yes. If you can translate the other problems, the new problems, into the stuff that you've been doing, it's the exact same process. You have the basic five things. You have angular displacement. You have initial angular velocity, final angular velocity, angular acceleration, and time. And then you pick out the angular cake formula, or the A-cake formula. What's a radian?
One radius
Keep going.
of a circle.
There's more to it than that.
Pi, like 2 pi?
I'm hearing things all related to it, but I haven't heard the connection yet.
It's like, yeah, what do you mean, what is a radian? Like, it's just a radian. It's the degree.
It's the percentage of a circle.
It's the sector formed from taking the radius along the edge of the circle and connecting it back to the center.
Okay, at this point I'll put you out of your miseries. Yeah, if you take the radius along the edge, it is the angle formed if the arc length is equal to the radius of the circle. So it's related to the radius, it's not the radius itself. And I think also heard it's the degrees, it's not the degrees, it's the radians. It's the angle. All right, so in this respect, this aspect of chapter 9 is the same stuff that we've been doing. However, let's get into the things that are different. Let's talk about Jita-Kabuka. Because it's physics, we're going to take something that all of you have been doing for many, many years, and we're going to analyze it, driving all the joy out of this act, because I'm sure all of you enjoy closing doors. So we're going to talk about closing doors. Unfortunately, this will be off camera. You know what? We'll see if we can actually rotate this thing. That would be crazy.
What is the angular velocity of the?
What was the direction of the angular velocity when I just rotated it?
Down.
Indeed. All right, so I want to close this door as effectively as possible. Instruct me. How do I close the door?
You push it.
Push it on its outermost.
Okay.
Let's push it on the outermost right there. I got that already. That didn't seem to work.
Does it have something to do with the tangential thing that Ian was talking about earlier? Like push it. Like, I don't know.
We want to push on the outermost edge of the front face. So
What's the front?
the one that would face in when the door is closed. I don't know how else to signify
I'm
it.
trying to relate that.
You can push on the tip of the doorknob facing it.
push on the tip of the doorknob.
Doorknob, yeah. See, that'll make sure you're on the right face.
Well, the tip could be anywhere.
Yeah, but pick the other one.
Okay, not the one I just did?
No,
So it matters if I push on this side or this side?
yes.
Okay, keep that in mind. All right, so I'm gonna push on, let's give myself some room here. All right, so I'm gonna push on this side. Here it goes, it's going. I don't know if it's sufficient, but it's going. Tired. Now, some of you hit it earlier. Where should I push on this side?
The furthest edge from
Like
the.
the
Furthest from the center of the,
Of motion.
yeah.
Axis.
Axis. Axis of rotation. All right, so push as far from it as possible on this side. You know there's gonna be something else here.
Oh, so continue pushing perpendicular to the door?
So like that. Are you satisfied with that?
Are you?
With more force.
That's pretty much it.
Okay.
So let's pull out of this what is important, and then, of course, how do we deal with it mathematically? Because it's physics. Something like that. Oh. That might be completely blurry. Not 100% sure how that's gonna work. All right, so there were three things that were important there. Okay, one, I had to apply a force. So, how hard, I guess I didn't mess with you on that one, but magnitude of force, the direction of the force, and where force is applied. Those are the three main things that go into torque. And so they came up with a nice little formula here that torque is equal to R cross F. So a couple things in my nice little notation right here. We are now dealing with a cross product. This is the other type of multiplication. So cross product.
What does the R stand for? Radians or radius?
It's a radial vector. This is known as the moment arm or the lever arm. It is a vector, thus the symbol for a vector, from axis of rotation to where force is applied. And then force, I'm hoping you're somewhat familiar with what a force is.
So you're gonna go into what a cross product is?
Sure. It's the exact same thing that you were taught in elementary school.
Okay.
So this equation is saying that you have higher torque the further away from the axis of rotation you are?
Yes,
Okay.
yes. It was just one of those coincidences that happened in life. I was teaching high school at the time and we were on this topic. And, sorry, I'll finish the story and then.
Well, what's that make force? So MEG?
Magnitude.
Magnitude.
Oh, yeah, magnitude.
And what's the thing on the bottom? DIR?
The upward direction. I could have summed that up, I guess, in terms of force. So I was teaching this topic in high school, to high school students. And there was a guy who was changing his tire, and he was using the lug nut wrench, what's that called?
Are you thinking of the T?
Yeah, it was one that was actually, it had an end like this, and then there was a little hinge here, and then you had a rod after that.
Yeah.
So, he had this on the nut, and he was trying to turn it like that.
But you can like move it, right?
Yeah.
Yeah, you can bend it.
And what that does, there's my axis of rotation, regardless. When he was out like this, two problems. One, the only force he could apply to it would be friction force. And the other one is that's a really tiny axis of rotation. You're not going to get much torque. By turning it up like this, one, you can make the normal force, the force, which is going to be more effective, but primarily you can make a much larger moment arm. So as R got bigger, the torque increased. Some students accused me of having made up the story, but it's actually true story. Physics helped. All right, another lesson. Sometimes you should listen to your parents or your dad, and physics helps sometimes. All right, so cross product, unlike the dot product cares about parallel components. The cross product cares about perpendicular components. So if I have A and B, and I want to figure out the cross product of A cross B, first off, let's talk about the magnitude of it. The magnitude of A cross B is, I take one of them, break it up into components, so break A up into components. This angle here is theta, so this is A sine of theta and A cosine of theta. And then I multiply the parts that are perpendicular to each other. I multiply A sine theta times B. So this would be A B sine of theta. Unlike dot product, which would be A B cosine of theta. Now, a cross product is also known as a vector product. For the purists, it actually produces what's known as an axial vector or a pseudo vector. But for what we are doing, and probably for the rest of your lives, you can treat it like a vector. There's some subtle differences that you can get into if you get into graduate level physics. So that means there's a direction to my answer. There's a vector symbol over the tile. How do you determine the direction of a cross product? Right-hand rule. You put your hand in the direction of the first vector, A. Now, I'm putting my hand in that direction. I've got basically 360 degrees of freedom at that point. I want it so that when I bend my fingers bend towards the second vector as efficiently as possible. I'm not doing that one with the idea that, oh, my fingers can bend all the way around. No, I want it to go as quickly as possible to the second one, so that would be bent that way. My thumb points into the board. So the direction of this cross product would be into the board. So A cross B would be AB sine theta, and the direction into the board. Using the notation we've used before, dot means out of surface, and the cross means into surface. And again, the memory trick is if the arrow is coming at you, you see the point. If it's going away from you, you see the feathers. Right. Questions?
Wait, how did you determine it was going into the board? Because
You put your hand in the direction of the first vector, and you want your fingers so that they bend towards the second vector. Your thumb right hand. And the thumb points in the direction of the resultant, or the product.
okay, wait.
Should I think about it with like my fingers pointing in the direction of the vector so that I know which one is furthest, or if that one's much closer because it's sort of angled down towards it? Is that how you do it?
Which ones?
Because, I mean, if you just put your hand straight up, it's gonna be the same distance no matter what.
Oh, you put your hand in the direction of the first vector, so it would be like that.
So it's already closer to B,
Yeah,
yeah.
yeah.
Okay, so. I think that kind of makes sense. Sort of.
So if the vectors are anti-parallel, the cross product would be
0.
0. So there's no closer way that either way you're closer. So it's always gonna be you want your fingers to bend the closer way to the second vector. If I gave you B cross A, same vectors, what was the direction of this B?
Would be out towards us.
Because B cross A. What's out?
Okay. So, A. Okay, that makes more sense. Kind of. Okay. I think I'm just confused because it's like, your drawing is 2D, so how is it gonna have a direction other than that? But I think I get it.
Another thing to point out is because the directions of the two, of A cross B and B cross A are opposite each other, commutative property does not hold. With dot products it does. A dot B and B dot A mean get the exact same answer. A cross B gets you the negative of B cross A. It makes a difference whether I'm closing the door or opening the door. There is a difference in what happens there. So just a quick example here, if I have a force, let's just do, I've got the overhead view of the door. And I apply a force at that angle right there of 30 degrees. And I'm applying that force, let's make it unrealistically big door. A 4 Newton force at a 30-degree angle from the door, and I'm pushing on this door 5 meters away from the hinge. It's a massive door. What is the torque being applied? Well, first thing I need to do is establish what my two vectors are. The force vector I think is clear. I drew an actual arrow there, but I didn't draw one for the radial vector. The radial vector is a vector from where I began to where I ended, so that's my radial vector right there. Now technically it would be from the hinge to where the force is technically applied right there. It would be slightly off, but good enough for what I'm trying to get across right now. And then the angle between them is, well, I've got one vector going this way, I got the other vector going this way. Is that 30 degrees or is that 60 degrees? And don't base it upon the way I've drawn it.
30?
With a question mark?
Yeah, I'm not confident in it.
Well, let's sort of extend this. So if that is going in that direction and that's going in that direction,
Oh, yeah, it should be 30.
that's the 30-degree angle right there, all right. So my torque is, the magnitude will be 4 newtons times 5 meters times the sine of 30 degrees, which is 10 Newton meters.
Are you pulling that from your torque formula over here? The like radial, the like moment arm times the cross product of?
Yes. So, and more specifically from this version of it.
Okay.
But there's a direction here. What is the direction of the torque? Well, this is R, and this is F.
It's into the board.
Into the board. So if I establish a traditional right-handed coordinate system, I, J, and K, it would be negative 10 Newton meters K. So a couple things here. One, Newton meters is not joules. When dealing with torque, a Newton meter is a Newton meter. I made reference to this being a right-handed coordinate system. So let's talk about why this is a right-handed coordinate system. A lot bigger here. All right, so I have I to the right, j up, k's coming out at you. What is I cross j? What is the direction of I cross j? Given, same thing written over there, just bigger over here.
Into the board.
And how'd you get into the board?
Like I that way and then J that way.
J is up.
Yeah, I'm not very confident in my answer.
Should there be a sign in there if we're following the same format as this?
All right, so let's do it that way then. We'll do the whole thing. I first asked what's I cross j, then I said what's the direction of I cross j, but we can do the magnitude also. So using the magnitude bit over there, it's the magnitude of I hat, which is magnitude of j hat times the sine of what's the angle between them,
90.
which is 1. So my magnitude is 1. Now it comes back to what is the direction. Now Brooke has ventured that it's into the board.
Wouldn't it be away from if I hat is first, we're moving towards J hat?
Yeah. And since I comes first, finger bends towards J, thumb points out.
Okay, that makes sense.
Now, this is a tool for trying to do this. If you have if your hand is such that your thumb can point back towards you or bend completely around, that does not change the direction of the vector. That is just an eccentricity of your hand. So it would be out. In other words, the k hat direction. In a right-handed coordinate system, I cross j is k. A left-handed coordinate system, I cross j is negative k. What is j cross k? Again, k is coming out.
Be into the board. Or wait, it's J cross K, one second.
It's I hat, right?
Yeah, that makes sense.
J cross k, k is coming out, so j cross k,